was sitting on the back of a deck of a boat about 20 years ago in southeast Alaska, and we caught mackerel and sunfish in our net. And I completely freaked out. I couldn't figure out what was going on. I started asking all the old timers around if they had caught these species of fish before. And in fact, none of them had. And so I started thinking about, what are we doing? And I quickly realized that it was fossilized energy, and quickly started thinking about our food system, and that a lot of our ammonia fertilizers are based on natural gas, and we're putting CO2 in the atmosphere doing that, and all of our food production is huge amounts of diesel, and so I started trying to think about how to make this system work. And one of the things I started thinking about was the cesspool and methane production on the dairy. And I started thinking, oh, well, there's some place where we densify nutrients, and maybe we can make that system work a little better. And always thinking about the economics of it, having it need to make money, right? So we can do enough work. The fact is that I can't rely on a grant to make this work. I have to figure out a way this works in the real world. And so that kind of started this whole process for me. And what happened is I was looking at those inefficiencies, and the ammonia's built up in a methane digester. And I knew carbon had a tendency to grab onto nitrogen. And so I thought, well, if I put a column of carbon next to a methane digester, maybe I could wash that liquid across that carbon. I could grab the nitrogen off, and I could make a fertilizer. I could keep the bacteria in the column longer, and my efficiencies would go up. And that's what led me to biochar, was that thought. So what is biochar? Because it was carbon, right? It was that carbon, and I needed to understand what carbon was. So essentially what biochar is you heat biomass up in a very controlled environment of low oxygen or no oxygen. And what happens is the cell walls tear apart, and the cellulose and hemicellulose release gases, these long chain hydrocarbons, and what's left behind is the inherent structure of the plant. So it's this beautiful matrix, right, that's left behind. If you think of the cell wall of the plant, when you've looked under a microscope or something like that, that's exactly what it looks like, only it's turned black. It reduces in size maybe by about 2/3, and this is what you end up with. The history of this idea comes from the terra preta soils of the Amazon. And what happened is in 1962, a man named William Sombrecht, a Dutch soil scientist, went down to the Amazon because he had heard of these soils. And as a soil scientist, he knew that these were oxalic clays, these were terrible soils, but there was these stories of these fertile areas in the Amazon. So he went down there to investigate what these stories were. And what he found was, in fact, perhaps the most fertile soil in the world. And when he started to do his digs and look around, what he soon realized is these were in kind of oval shapes where these soils existed. And around the outside of the ovals was the parent soil, and it's this oxalic clay. It's very poor soil for growing, our plant species for agriculture. And then as he came in towards the center, he saw what they call terra mulata, which has a high char amount in the parent soil, and it's more fertile. And then in the center part was the terra preta. And terra preta, the Indio, means dark earth of the Amazon. And when he looked in there, what he saw was a very large amount of charcoal and shards of clay pots, bone matter. It was clearly anthropogenic. This was clearly soil that was made by humans, and it was soil that was thousands of years old and still held on to its fertility. And so he quickly started thinking, well, why is this stuff so fertile? And he came to the conclusion that it was because of the high amount of the carbon in the soil. So we can move on from there. So this is kind of a picture of kind of the difference in, this is from Christoph Steiner, I think, took these photos. And basically this is trying to grow in the parent soil, and here he grew some corn in the terra preta soil. And they in fact, people down there mine this soil and take it into the cities for their raised beds and that type of thing. So this is just another kind of definition of what it is, and some pictures of what we're looking at under a scanning electron microscope, just to give you an idea of the matrix of the plant. So it kind of gives you maybe a thought of what's going on in there. It works very nicely for a home for microbes. You also get these charges that exist in there, and the charges can be positive and negative charges. That can vary, and I don't need to go into the chemistry of it, but the upshot is that it also works. It also can work as a liming effect, but it helps the tilth of the soil. Okay, it helps with nutrient exchange. It helps with slowing the loss of nutrients as they flow through the soil. You know, that's what we're seeing. So how is biochar made? This is from Tom Miles. This can be like an industrial process, kind of like where I work. I work at a timber yard. And you know, this could be something, a flow chart that might be worked out here, like where you have a biomass composting facility. About 30% of the screenings are going to be high carbon that you're not going to be able to really chip up. That you're not going to be able to really compost, and that could be your process fuel stock for carbonization. This just gives you an idea of that it is going on around there. You can do it with different feedstocks. It's very scalable, and that's one of the things I really like about it. So while you can have these industrial processes, I really like the idea of these stoves. You can have these pyrolytic stoves. Most of the people in the world still cook on a 3-stone fire. And it causes emphysema. Women and children all over the planet are dying of emphysema because, you know, they're inside their houses cooking on these 3-stone fires. You can have these simple cook stoves that actually will make char in the process. They can cook their food, and then they make charcoal that they can put on their poor soils that surround them. Generally, in these impoverished areas, you have very poor soils. So it's a nice marriage of technology and need. This is just the feedstocks. The feedstocks, to me, is very important. You'll hear people talk about this being a carbon reductive form of energy production. That's true if you do your feedstock sourcing right. It's never going to make sense to make biochar out of primary forest. It's waste material. You know, this is a picture at my log yard. I mean, I think I've got some more later if you want to see. And I did a small survey, and I had 6,000 tons of biomass just laying around that was rotting. And if we think about the life cycle of carbon in the atmosphere, essentially what we're doing, you know, we know fossilized energy is carbon, you know, puts carbon in the atmosphere. Ordinary biomass fuel, where you drive it all to ash, is carbon neutral because all the CO2 that was taken up, all the carbon that was taken up in photosynthesis is then released through combustion back up into the atmosphere. Now, when we do carbonization type of technology, I can actually take the material and yield energies, but I hold on to a certain portion of that carbon into a stabilized form that doesn't break down, that has half-lives in the order of several hundred to several thousand years. I think later I can probably go into the chemistry of why that is, but the other idea is that there's this feedback loop that's possible. So if we look at this going on like in the Amazonian frontier where there's this forest being destroyed, a lot of that forest being destroyed is because the soils are poor, they slash and burn. When they burn that, it does put some minerals back into the soil, but they quickly burn through it because there's no carbon to hold on to the nutrients. So they move on, right? They move on, they cut more soil, more forest. Now, if we were to take this and carbonize that material, we would actually create a healthy soil. They wouldn't need to move as much in that environment. You'd actually increase net primary productivity of that area. So the feedback loop becomes, you build the soil, you start to grow more material, you have an ability to then take more material and carbonize it again, you know, spread out to further soils that have already been denuded. You can start to increase the net primary productivity of the entire region. Because in those types of soils, you know, the yields are quite substantial in a very poor soil when you start to include this type of carbon into it. We've documented time and time again in the very poor soil, net primary productivity going up 120 to 200%. You know, we're not going to see that in our rich garden soil, but when you're talking about that oxalic clay that I showed you, that is in fact true, and we have paper after paper that shows that. so the reason I got involved in this as a scientist was that the potential was so fantastic. Everything that I saw when I looked at it, there is a tendency to look at biochar and think of it as this, oh my God, all of a sudden I can save everything. It's the black panacea. But I don't look at it that way. I look at it as its potential. That the reason we need to look at this is because the potential is so fantastic that we need to dig into it and understand what it is. It might not be that everything we think is possible, in fact, happens, but there's so much that is possible that certainly within that we're going to find it. And so we're talking about food security, energy security, job creation, water cleanup. That's something I've been really focusing on, is the water cleanup. And all those things are very possible with this material.
Could you say how this material helps water cleanup?
Yeah. The reason it helps water cleanup is it's a complex material, but because of the charges that exist in it, it'll bind metals very well. So if you got these +2 heavy metals, right, like zinc, lead, I can't remember the charges of all of them, but copper, it grabs a hold of them out of the watershed. So when I take my material and I put it into a stormwater type of situation, it grabs onto those. It also grabs onto hydrocarbons really well. Like what they could have done in the Gulf is to spread char over it. We did that experiment. Actually, I took an aquarium, put a bunch of oil in it, put char in it. It just sucked the oil up, and then it still floated. We could then take it back off. It also does that with polycyclic aromatic hydrocarbons, so PAHs, which are ubiquitous in like harbors or where there's any kind of fuel depot. It's full of these PAHs, like toluene. Ben, you know the names better than I do, but it nasty stuff, But this stuff will suck it up, and with the PAHs, what happens is it sucks it up, and then the benthic community will come and then consume it and break it down into its component parts, basically CO2 and water.
So it's even more than a filter. It's even more powerful than a filter.
I've seen it work better than granulated activated carbon, because there's activation sites still on it. So I have the chemistry, like with granulated activated carbon, a lot of what's going on with the binding up of those materials is just inherent in the pore space. There's just so much pore space with granulated activated carbon. Basically, that activated carbon is char that they've hit with steam or hydrochloric acid or something like that to open it up even further. But in doing so, they've taken away a lot of the activation sites, the activation energies that are possible. With this, that's still on there, and those can be manipulated. We can manipulate those through process and through feedstock. So we can start to create these designer materials, and we're working on that. Me and a man named Dr. Marcus Kleber, when we were looking at this, started thinking about, okay, we need some specific research goals. Now, first of all, biomass is going to be used for energy, and again, we need to make money doing this. So this is one of the things, is that we have to, in my opinion, find value in the heat production or in the gases that we're making somehow. Okay. The next thing is that we're going to, for me, this is a marketing thing. This is something that people are going to feel good about. It's in fact true, but I'm not expecting money for this, right? And so I can sequester carbon, and I can tell people I'm sequestering carbon while I'm making energy. But we have to prove that. We have to do the full life cycle analysis of how the material is being moved, how we're acquiring it, where we're locating the machine. And then the third thing is that we're going to improve the soil or improve the environment somehow with the material. So that's how we find the real value of the carbon, right? So I'm not expecting to make carbon value from some offset. I'm expecting to actually make tangible carbon and find value in that for society. And that's how I'm going to make money with carbon. So this is just kind of showing that there's differences in the chemistry of these materials, that everything that's black that you get out of your fireplace isn't necessarily the same. They're actually quite different, and that's an important thing if we're going to use it. So I don't really need to go into that, but these are just different temperatures and different materials of wood and grass. And I got a couple of charts that show maybe what those differences are So this was done by Dr. Johannes Lehmann, who's just a fantastic researcher in biochar and a lot of other things. But what this shows is a parent material, and you've got carbon recovery, the pH of the material, the cation exchange, and then the surface areas. So what happens as you're going through this charring regime is that you get this optimum spot, or you can see things change. And what happens is as you heat it up, it goes through this area called torrefaction, where all the water's been driven off, and you start to get cross-linking of carbons. And then all of a sudden it kind of breaks free, and all of these things take place. The surface area goes up, the pH rises, cation exchange increases, and this carbon recovery, the amount of carbon in it is going to, I guess I'll go to the next slide, describes this a little better. So right here, when we look at this, there's always an inherent amount of carbon that you can make stable in a given amount of biomass, okay? And what happens is the carbon can either flux into the atmosphere by rotting or whatever, burning, or that lignin part you can stabilize through heat regime. And that's what this is. So the amount of, so the char yield total will go down, but there's a lot of what's called volatile or labile carbon in that potential, and that stuff's always going to get lost. But you can hold on to it. You can hold on to about 30% of it if you stabilize it. What this is showing what that turbostratic crystalline char is and where it shows up on the temperature. And the reason I put that up there is just to kind of show that we're getting an understanding of what the material is. I don't know if you want me to go into the chemistry of it. I don't know if you guys have any questions at this point, and I'm happy to take them.
Yeah, well, maybe I was just going to make a comment that just always helped me think about it, and correct me if I'm wrong. But the way you actually make the char is through pyrolysis, I think you mentioned, which is basically just containing it in a way that no air gets to it and heating it up. And so you're showing that graph with the different temperature ranges. You got to kind of think of it, if you were to put a piece of wood or some brush or something in a chamber and heat it up, at first it would be kind of like sooty and, you know, start getting brown, and eventually, right, it goes through that whole range, and at some point all the different oils and stuff basically vaporize, and then you're pretty much left with the cell walls, the toughest part. And then, you know, the hotter you go, the more that stuff will basically become more and more of a crystal, right? And that's basically like, if you went to a really, really high degree, you get like, I don't know, you get graphite, right? Which is basically what your pencil is. And so that's kind of interesting. I thought that's a good way to think about it.
So what happens in this is when you have biomass, you know, it's a bunch of carbons built with a bunch of hydrogens and oxygens linked off of it. And when you're heating it up, those hydrogens and oxygens are getting driven off, and that's what you see burn, and there's carbon in there too. That's what you see when you look at the fire burning, and above the log at first, there's kind of a gap, right? That's the pyrolytic gases, the pyrolytic tars and oils is what burning. And as that gets consumed, then it goes into the carbon, and that's when the coal starts to burn, and you start to actually burn the carbon away.
So you had asked if you should go into the chemistry. Before we go deeper, do people have questions about this? That's a lot of information. Anybody have any questions? Because this is supposed to be interactive.
Yeah, I don't mean to take up all the time.
No. It's fabulous information, but I see one question here.
Well, without getting into the details of the chemistry, to me it sounds like if you're producing energy from it, it would have some pretty nasty effluents. So could you comment on that?
Effluents like gases, oils, tars, those types of things?
Anything.
Yeah,
I'm just,
that's why I was, I don't know if I said it, but it's really important that you have control of the process, right? So that the gases that you're making, you need to have them go through a flame front. And once you put them through a flame front, you are making nasty gases, there's no doubt. But once they go through a flame front, they disassociate and they become hydrogen, they become water and CO2. If you have manures in there, I have some question about the amount of NOx that you're making. That's something I'm investigating and trying to understand more. But if you're using biomass, wood, and most grass species, all you're yielding is CO2 and water vapor, because if it's gone through a flame front. And the toxins can come out in the oils and the wood vinegars that can be, if you're condensing that gas. So that you need to have control of and understand what you're making. You know, there are people that are making the bio oil and the stuff they're calling wood vinegar, which is pyrogenic acid. It's interesting chemical building blocks, but like anything, there's you know, any kind of densified, you know, think about all the crap we spray out there. I mean, that is toxic, nasty stuff. And absolutely. So if you're gonna do this, you have to have control over what you're doing. You know, but the backyard kind of biochar thing works fine, and we can explain how to do that, and if it's going through a flame front.
So one of the ways to think about this from a common perspective is if you have a campfire and the campfire is roaring, really burning, there's almost no smoke coming off. Once the fire starts to die down, you get a lot of smoke. That smoke is actually uncombusted hydrogen and carbon chains, and that's what's actually polluting. So when we have no burn rules for fireplaces, it's because we don't have a clean burn on that biomass. With the pyrolysis equipment that's being developed now, it's much more efficient, so you're getting almost 100% clean burn on the off-gassing. So the air quality is very clean. When it comes out.
I have EPA out at my facility all the time. I've encouraged them to come out, and they're very, you know. The other thing is the particulate matter on a well-designed machine is quite low, because most of those particulates that you see go up that are uncombusted carbon are that lignin that we're trapping.
I'd like to interject one more thing about that. When you're making biochar, if you're making it on a commercial level, these gases that are coming off of the wood as you're cooking them out of the wood are becoming used to make the heat, to become the thermal drive for the process that sustains the reaction to make more biochar. Okay? So as all these gases come out, they get burnt, they get turned into heat, and at that point, rather than going into the atmosphere in a more toxic form as methane or something like that, they go into the atmosphere as carbon dioxide, nitrous oxide perhaps. These can be controlled though. So one of the benefits of making biochar is making heat. And our intention in the biochar facilities that we're designing and intending on building in Oregon will be to take advantage of that heat and use it for a positive benefit for supplying the heat needs to municipal buildings, refrigeration, making energy, and so forth.
I've got two questions, one semi-technical and one semi-business. So is the difference between this and an ordinary fire controlling the amount of oxygen that goes into the fire?
Essentially, yeah. This is what we would call stage combustion. So we're controlling the amount of oxygen where, right? So I have either no or very little oxygen in one place, and that's where the biomass is, but I have heat there, right? If you think of that Boy Scout triangle, right? Here I don't have the heat. Or here I don't have the oxygen where the biomass is. And that gets heated up, and then those gases get elucidated out, and I combust them separately, and I use them someplace else where I can use them for whatever I want.
So is this part of the continuum from an open fire in your fireplace to a really well-made wood-burning stove where you're really controlling the oxygen and the vents and the recirculating? So it's like a great wood-burning stove compared to an open fire, like on the way to this?
Yeah, like the really great the great stoves that are very clean, they're reburning those gases, so they cycle back in to the burn. And so like if you look at inside of those stoves that are burning, you'll see a lot of flame rolling along the top. That's because they're taking those gases and they're rolling them back into the flame and burning. So that's why they're burning so clean, because there's kind of a pyrolytic action going on in there.
So that was the technical question, not the business question. Since this looks like a really fantastic thing for a lot of different reasons, and you've been careful to try to qualify it and say potential and more research needs to be done, where are we in this process? Are we where the homebrew computer club was in 1970, wire wrapping things? And is it going to take 40 years to get to the home computer that you just buy from the Apple store and bring home and turn it on? Or are we like 5 years away or 50 years away, or do we not know where we are because there's a lot more fundamental research that needs to be done?
I was saying earlier that as a scientist, I'm always kind of saying, well, we don't know or whatever, and I can get in trouble that way. We know enough that this is very useful material that I have been deploying it, right? I've been using it in for cleaning up water, like I was saying, and we're finding a lot of success in that. I've been using it in my own personal composting, trying to encourage others to do that also because I find success there. It's a complex, that being said, it is a complex material, so as you know, this researcher geek, I'm always like, well, but I don't know. So, you know, I guess the upshot is I think we're getting to the place where there's, you know, there are little startup companies doing it. So I would say we're kind of at that Wild West part of the equation you were just talking about it when computers. So I don't know, Gates is probably just stepping out of his garage. You know?
I did a study a couple of years ago in 2009, and at that point there were about 80 biochar companies, and only a quarter of those actually had some sort of product that they were selling, whether it be a technology or a biochar product. And then there's about 40 universities studying it, and then another 40 nonprofits. And that was in 2009. I think there's a lot more now of the nonprofits, and I think some of the businesses have merged or been acquired or otherwise shifted hands, but that's about, in terms of numbers, where the space is right now.
So if you project the data that you accumulate, does it look like in 5 years this should be like pretty mainstream, or is there a ton of expensive research that needs to be funded in order to find out if it makes sense?
I'd like to see it become mainstream because I don't think we have really enough time for it not to be. I think there's an urgency to shift our agricultural system around, and I think this is an important component in making that turnaround. I think there's like some specific research that needs to be done, like John was saying, there's designer biochars that can be highly researched and designed for specific cases, and those might take a couple years. Biochar you can't see in 1 year in a field test all the implications of what you're applying. I mean, you can take 25 years to really understand what's going on in that soil because it is such a long-term stable additive. So, yeah.
Another perspective is there's a continuum of operations. So everything from the small cook stoves in developing countries that Mark's working on, and there's a number of companies that are working in that space, and very viable companies that are both profitable and social entrepreneurial kind of profit generating companies, all the way up to heavy industrial operations that are doing cogeneration of electricity along with bio-oil, and there's a company in Iowa that's looking at asphalt developed out of the bio-oils from this process. So you have everything on that continuum. There are viable economic activities on everywhere along that, from the local farm scale to the industrial farm scale to the industrial scale. So it's more the technology is there. There's a refinement going on in terms of the technology, and there's a lot of development in that. But it's not like there's a discovery that needs to be done. So it's more of an adoption issue at this point than it is a discovery issue. On the scientific side, because of the complexity that we're talking about now, there's a lot of work that needs to be done that's important to be done, but it's not necessarily a limiting factor. One of the things about we are carbon beings. I mean, we're carbon-based beings, and we eat carbon-based food, and so the technology itself is as ancient as the Earth is. So as long as there's been biological systems on carbon, that carbon, some of that carbon has been stabilized through heat and fire and has been integrated into the natural systems. So what we're talking about is using our human ingenuity to take that and apply it to a modern context.
So would you say then it is scalable enough to be fundable?
Yeah.
Yes,
Yes.
Definitely.
absolutely.
You know that right now the good thing about this organization here and this format and the idea of sustainability, and I'm going to use your idea of sustainability, Howard, fixing problems faster than we create them, is that the dialogue that is happening between people in situations like we're in this room is something that we will be seeing more of all the time. And one of the challenges right now is the challenge of the relationships around policy versus practice. And if you want to pick one sector of the carbon industry right now and look at biomass, the idea of burning biomass to make energy is so attractive right now. And the reason that the practice and policy are together on that is that energy tag has been put on that subject. And so right now, if we all went on a field trip tomorrow and we took this around the Pacific Northwest, we would find biomass energy plants dotted across the Northwest. And we'd find them in a couple of different distinct types of operations. One would be upgrades of industrial processes, paper mills, things like this that need heat. They traditionally take stuff called hog fuel, which is unmerchantable wood chips, burn that, make heat, make steam, helps run their industrial process. Well, a few years ago, we decided that for biomass energy, that we would subsidize these things federally. And so what we're seeing right now is the use of this biomass through burning to make energy. And what we're talking about here is the same thing with an added benefit. And that added benefit is that we get a useful product out of it, and then that we're also taking carbon out of the atmosphere. We're doing a, what did you call it today? Carbon reduction, energy production. This is what carbon negativity is. Rather than burning a tree, sending it back up into the air, plugging in your electric device into your wall at home, and enjoying the benefit of that carbon and not doing anything to take it out of the carbon cycle, by creating biomass energy plants, that the centerpiece of which is a biochar plant, we're able to take some of that carbon out of that cycle and gradually reduce the amount that we're putting back into the air.
So we've been talking about the supply side. What about the demand side? Is there, so if, you know, is there a market for this biochar that I can then take and sell that? Is there a big demand for this product?
It's growing, you know, I think it's not that many people know about it, right, or its uses. One of the places where I've been getting a lot of traction is in water remediation. In Oregon, there's been kind of, you know, from the industrial landowner's perspective, kind of onerous, you know, regulations come down, right? And so, like, you know, I talk about zinc quite a bit because it's the #1 metal toxin in our watersheds, and it's quite destructive to trout species. But there's a thing on the DEQ in Oregon just came out 2 months ago, and they dropped their threshold from 120 micrograms per liter of zinc down to, I think, 86 or something like that. Well, all of a sudden, people that were making benchmarks can't make these benchmarks anymore. They're getting fines. And the people are getting looked at are these industrial sites or like a warehouse that's their stormwater. And for them to handle that is quite expensive, you know, because the current technology is, for a vault with these filters in it, is $50,000. To re-roof their roofs is, you know, a couple $100,000. And then we can come in and for fractions of that, put some carbon into this system and take care of the problem. So there is some market research that needs to be done, and we're doing that through the university and also through just some private kind of like what's out there work. That's one space where it can be used. When we take char and we start to add nutrients to it, like in-house, like if we tie it up with, say, a methane digester, a char production and methane digestion, and then we start to grab into those nutrients and we can start to move those nutrients around, there's value there. But that market does have to be built. People have to understand it, I think, a little better.
Is the EPA supportive of this?
Yeah, the EPA in Corvallis has been very supportive. They've looked at both from the carbon reductive aspects and the metal cleanup, and we've been very open with them about testing the material, being very forthright with what is this material. We're here it is. Come look at it. Do you see any problems? And I think they've appreciated that. And so, in my experience with the EPA, has been surprisingly they've been surprisingly supportive.
So you're saying there could be legislation accelerated adoption?
Oh, that would be great. Yeah.
if legislatures pass standards and there isn't another way to meet them, then that is going to accelerate the adoption.
Yeah, I think so. I mean, that's what I'm seeing in the stormwater. I just dropped off 14 yards to the U.S. Department of Transportation because they're looking at it for banding along the U.S. highway system. I just dropped off 7 yards to the U.S. Forest Service because they're looking at trying to build up water holding capacity, and they're also wanting to look at being able to do fuel load reduction in the forests. The southern Oregon's about to burn to the ground. You guys have had plenty of fires down here. We've got the same thing in southern Oregon. We've just been lucky, and they're very concerned about it. And so, they're tying in with the U.S. Highway Department, to see what the potentials are for filtration work.
So what does the yard of this go for?
It's all over the map, but I've seen it for anywhere. Well, see, the problem is that the weight can vary quite a bit. So people are selling it by the ton. I usually try to move it by the yard, and a yard's around $300, something like that. That price point can drop down quite a bit. So there's people selling it for $1 a pound, so $2,000 a ton, to $600 a ton, and I still think that price point's kind of high. It's early. I would like to see it come down some more if it can be used, but that's my own bent, Yeah.
So it's clear that it's useful as you're looking at a closed system growing space as an import of what's a waste material outside of the system to bring fertility to that piece of land. Is it so useful that it's worth taking your own waste, which we don't consider waste, we grow our carbon crops in order to compost them?
Yeah.
Is it so useful that I should be burning the grass refuse that I usually compost in a cold compost so that I keep as much carbon in it as possible? Should I be burning it, or should I be burning a part of it? Like where is it?
I would personally say like your grass, that I would compost, but I would take wood clippings and those types of materials and carbonize them and put them in with that compost. You're going to hold on to more of your nutrients. You're not going to have as much phosphorus loss. You're going to see a holding on to nitrogen from 50 to 80% more by including it in your compost.
So I'm curious about two things. One, you mentioned carbon filters. There's already a market there. How is this different? And the other thing that strikes me is they found this in ancient Amazonian practices. Are we trying to rediscover how they made it, or is that a known thing, how it got there?
Well, there's conjecture on how it got there. So what the thought is that however the process started, what the people there realized is that this was fertile. What they were doing was taking the kitchen medians, like the waste from their kitchens, even their own waste, taking this is Stone Age, so they're not cutting down forests. They're taking out some of the debris from the forest and they're charring it with their waste. And at some point they realized this was very fertile.
So we're rediscovering.
we're rediscovering it, and we're certainly not making terra preta yet. If somebody calls their stuff terra preta, you know, I would say they're full of.
Really, we're not there yet.
No.
But the activated carbon filters, that's a different target. I mean, that sounds like it's already a market.
I think, well, what I'm seeing is I think a lot of the activated carbons, they're over-engineered materials. You don't need to go that far.
Over-engineered. I see. So that is a market, but they're not a big market, and it's overly expensive right now.
Right. I mean, you're,
So you look at the
for a ton
product.
of activated carbon is $7,000 to $12,000.
I see.
So you can't use that material to do all this remediation work, because a very limiting factor is the cost of the material.
Another thing is that as we're making these materials, we're making them out of different types of feedstock. And then depending on how they're made, what feedstock they're made out of, they have different highest uses. For instance, one of the chars that John made for an experiment that I've been working on with an environmental testing group was using this as a remediation application for treatment of sediments that are contaminated at a Superfund site, trialing it against a couple other very well-known and well-used remediation compounds. The biochar outperformed them. It was something that dispersed at a very low level within the sand cap that was placed to contain the contaminants that were in the sediment, and it fostered biological activity, and it prevented all of the escape of the hydrocarbons that have been percolating out of it. Now that was a real specialized char that was made out of a digestate that came from dairy screenings. And so that would be similar to the type of char that could be made if you had a plant down here that was combined with your plant down the road to be used for cleaning up contaminated soil, sediments, things like that. But by the same token, we could make chars out of nut hulls that have the capacity of passing water through them real well, because they don't pack good, and those are great filters. And you can just use it for all kinds of things. Yeah.
For industrial air.
I'm gonna comment to what she was saying about like, you know, do you want to compost the stuff that's on your little garden or on your farm? And when I was looking into this, one of the things I discovered, which I did not know, is that a lot of these farms out, you know, in Iowa or somewhere where they just grow a ridiculous amount of corn per acre, they have so much cellulose, so much carbonaceous material that it doesn't compost. And if they were to put it back on their fields after a couple of years, they would just have like so much of it. So I think what they do most of the time is burn most of it. They just pile it up and burn it. So that's like obviously not very useful for anyone. And so I think that's an interesting area. And I think they do the same thing with forests, like you're talking about, to keep the forest from getting too dense. They just pile them up into these piles and burn them. And that's
We're required to burn them.
It's the state of the art at the moment.
And we don't have, by the time we're done with the cut, 30% of our, our hillside or whatever is covered in a slash pile. And so we want to go and replant, but we're actually required to burn by the Department of Environmental Quality to suppress disease. So, as much as I like a bonfire, it kind of breaks my heart every time I go out there and light them off. It's just like, it's a huge waste. You had a question.
Yeah, sorry. I actually don't grow grass. I grow wheat, sorghum, quinoa, these things that are somewhere in between. I mean, they're not woody, but they do have quite a bit of the structural carbons in them. And that's kind of where my question is more.
Right.
It's not, I mean, it doesn't make sense to me to burn something green and full of nitrogen like a fava leaf or a green grass, but.
Right. But I would say maintain your carbon-nitrogen ratio, and then if you have more carbon still available, certainly carbonize that and put it into it. And if you don't have it, I would acquire it and carbonize it and put it into it. Yes?
Since you were mentioning over-engineered materials, you always read about new forms of carbon are going to, this is the one that's going to make the killer battery electrode. Have there been any research in this. I've heard, for example, that pyrolyzed chicken feathers make great electrodes.
Right. Yeah, I mean, absolutely. We're looking at those types of uses of this material. We're looking at being able to take it and make acetylene. You know, that was another little bit of research. So yeah, I mean, all of those things are being looked at by you know, other researchers than me. My concern is water and soil. So I can answer those questions more. I mean, I've seen those other papers and kind of look at them and think, oh, that's interesting, but I don't really know a whole lot about it. This is just a description of why the material is so stable. So essentially, this is the plant after it's gone through, like, maybe just past torrefaction, and you've driven off a lot of the hydrogens and oxygens and the outlying carbons. And what you end up is with this thing that's called a benzene ring, and there's some hydrogen sticking off of it. Now what happens as you continue through the carbonization, those hydrogens get torn off, right? Those hydrogens become part of the gas that you're burning. And this carbon needs to fill its 4 valent shells, okay? And so what happens is it swings around and it grabs this other carbon, and all of a sudden you've got all these double carbon bonds. And so what that means is that it takes a lot of energy to break that bond. And it doesn't behoove the wee beasties to try to crack into it, so they just leave it alone. And so it sits there. And they use it more as a structure. I can kind of go through this stuff. We can skip it. So while we talk about it being a very stabilized material, what happens is there is some breaking down. Okay, so the edge structure will break down, and you get oxidation show up, and then you get these activation sites. Now, these activation sites can also show up because of minerals that maybe were inherent in the biomass. So this is like, you know, this is biochar in a lab. Okay, so this is like the vacuum of space or something. But the point I want to make is that we do get sites where we get exchange of nutrients, and those are the places that I can grab onto metals and toxins or nutrients or those types of things. And so you get a chance for ionization energies and whatever. I don't think I need to go into the chemistry of all this. So we've been looking at better ways to analyze it, because some of the ways to analyze it are quite expensive. So we started looking at XRD scans, and what Dr. Kleber again recognized was he saw these humps here, and these humps are indicative of stabilization. So what happens is, as we carbonize the material and we get those benzene rings line up and they start to pull each other in, it starts to stack up like a deck of cards in height and width.
What are these 2 axes?
This is, I'm sorry, I'm not going to be able to answer that question. This is Marcus Kleber's work.
Are the humps
spectral
prominences indicating
these humps
that are present?
Yeah, these different humps are going to be different minerals that might show up, and also this particular one is the shape of the height and the width of the lattice work of the biochar.
This is time and temperature.
Time and temperature.
Time and temperature
Okay.
are the 2 axes.
And well, is it time and temperature and XRD?
Temperature, isn't that on the bottom? What's the bottom?
Is temperature, because
I think it has to do with the X-rays. It's X-ray diffraction.
Oh, okay.
Well,
frequency.
yeah, it's frequency.
Yes.
Along the bottom is frequency. This here, actually, I think.
Yeah.
Anyways.
Transmittance or something.
Anyways, so what Marcus saw was these humps here, and he correlated them to the height and the width and the stability. And it was another indicator to us that we had some more understanding of the material. And the other thing he noticed was these quartz and carbonate signals, and to him that was really interesting, because those can be amphoteric material. So what we can, that starts to explain why we're starting to see positive and negative charges on the same material. Because carbonate and silicates, they'll change their charges depending upon the alkalinity or the acidity of the environment right around them. This is just, again, looking at, I guess, the different chars that I was making and the differences in it. So what this is looking at the top, this top band. This is a soil that doesn't have any carbon in it. And this was in a column. And there was water, deionized water went through it. And this is cadmium, arsenic, and zinc. And what you can see, I think, is that there was more cadmium, now less cadmium, right? And so what that indicates is, like, if this was in next to a watershed, the water would now have this material in it. So then underneath of that is a column that had carbon involved in the soil. And then the leachate went through it, and this was 5 weeks later, and you can see that it trapped it.
It trapped the cadmium in those chemicals.
Yeah, the carbon grabbed a hold of them, and now we can see them in the column. So this is kind of just a little bit of a recap of what, you know, I guess I've gone over this too. It really can greatly improve the physical structure of soil, and in doing so, by improving the physical structure, you get all these other benefits around it. Like if you think about a clay soil, that when you put char into it, the clays generally are these platelets that are laid on top of one another. And the reason, while there's inherent nutrients in clays, the reason they're not available to plants is because there's no gas exchange. There's no way for, you know, humic acids to get in there, and there's no. But once you put the char in there, all of a sudden, you know, you get tilth. The platelets start to line up around the char because of charges. Is a lot of it, the electrical charges that exist, and we can see all these kind of soil health benefits.
Do you have to till it into the soil?
You know, I think the way it should be agriculturally applied is actually ripped and injected is probably the best way. You can put it on the top, and over time it will go into the soil. You know, what we've seen is actually worms like it quite a bit, and worms will actually ingest it and you know, get rid of it and move it around. So if it gets into the soil, you'll actually see a lot of translocation from the soil biota moving it around. I would encourage, if it gets put on the top, to either, you know, you want to wet it first because it can be quite dusty, or cover it with, you know, straw or something like that. That's one of the things that we're kind of struggling with in the forestry industry, is how do we apply this, broadcast it, or whatever, you know. So here's some of the markets, you know, that are available. One of the things that we first started looking at because you know, we grow trees, is the vermiculite replacement. So in soilless media where you're growing plants, you have this material called vermiculite, and basically what it is, it's a bulk soil ameliorator. For gas exchange, or it does do some cation exchange. It's a tremendous carbon footprint, and it's quite expensive. A ton of it costs about $700. It's generally mined in South Africa, China, and then there's a couple, I think in Pennsylvania, there's a couple places on the East Coast, and then it's mica that's then brought in to a central location, ground up, and popped, like exfoliated at about 1,000 degrees C. So it's got this tremendous carbon footprint. We've been using char for about 3 years to grow trees. Had really great success with it. The other thing that looks kind of interesting is in turf grass, like golf courses or for parks. You can use quite a bit less fertilizers. We've seen, you know, we can reduce fertilizer by about 50% and still get the same yield. Soil remediation, and water, that's something I've really been focused on, because it's both lucrative and it's I think getting metals out of the watershed and hydrocarbons out of the watershed is very important. I think broad scale agricultural use is actually going to be the last thing on the chain where char is used just because of the price point right now. You know, if we can get the price of production down to, you know, $200 a ton or something like that, then I think we can start to see it used in broad scale ag, but we're not quite there yet.
What is it now? Where are you two?
Well, that's what I was saying, it's up and down. My personal production facility is really like a giant bench scale production. I don't know that it would ever be, I made it so I could start to understand the material. So I don't know, my stuff probably costs, if I was actually gonna charge, probably $4 or $5 a pound, something like that, if I was gonna, you know. But I basically.
So $8,000 to $10,000 a ton.
Well, that's what I'm saying. My facility is, I've made it so I could make the material. I'm not trying to make a production facility, but you know, I think biochar solutions, they're selling it for $1 a pound. I just got a phone call today from Phoenix Energy, who has a truckload that he was looking for, you know, a home for, and he was like 50 to 30 cents a pound. So it's all over the map, really. And I think that's indicative of its newness and kind of where the technology's at. It's very scalable, and so it's really a lot of, we're at like building the market still. I mean, I'll be quite honest about that. That's why I've been investigating the stormwater market to try to really see how big the market is. You know, I go to these places and talk to stormwater guys, and they say, oh, it's huge. And well, that doesn't really do me a lot of good to know what, you know, I got to find out what huge is. So I got funding for a couple of grad students, and we're working on what huge means. But
you need a killer app.
Yeah. Yeah.
You know, I've read things about future materials. They're not really future, but carbon fiber and graphene, which I saw in one of your things. Mm-hmm. Is that a different? I think those are made from petroleum now, because so is that just a different order of magnitude of intensity, or do you think the things you're making might actually find a market there too? Because you know, from what I've read, those are, you know, going to be great, going to be in high demand.
Well, it's the same carbon. I don't do. Yeah. I mean, because I can make carbons that are 92% fixed carbon. You know, so I can make very high carbon material.
I think that part of the issue would be to have a product that is real consistent, and I know that the history of the activated charcoal industry in this country includes the making of it from nut hulls, from the nut farming, hazelnut, walnuts, and so forth. I could see potential there for that at some point, you know. But this is something that for us we're really focused on a different, more developing a common market for it.
The lower grade application.
Yeah.
I have a question from a time perspective. We're roughly 90 minutes into our 120,
okay,
and you haven't had a chance to like take the stage yet. I don't know if you guys have worked out the passing of the baton part, but we're 3/4 done with the time and 1/2 done with the people.
Well, I could quick go through to
important ones.
Well, this is just some of the remediation work we've been doing. So this was out by my house. This was around my house is Jory clay. It's not very good for growing plants on. This was sitting like this for 10 years, and then we put together a company that I work with making char for us, Sunmark Environmental. We put 10% char into a mix, and they really that was about a month and a half after that. It's pretty dramatic. It kind of speaks for itself. So I guess this is something I wanted to get to, and I kind of spent too much time on the others. My background's integrated systems, really. It started on the fishing boat because this was an integrated system within the ocean, and started me thinking that way. And I think for biochar to work, we have to plug it into other places. Where's there a heat user that we can supply heat to? So green industrial parks, which is this. So this is Dr. Ogawa out of Japan. Kind of gives you an idea of how this system could work. You know, you've got these crops. You know, he's talking about some kind of plantation crops, which our forest is basically a plantation. And it's just, the idea, the reason I put that up there is because it really, we need to start thinking in these integrated systems. These whole systems thinking is the way we're going to design our way out of this mess. This is an overshot of our log yard. This is where our log yard is. And the reason I went to Thompson Timber and started talking to them was because of revitalization of infrastructure. So sitting out there was an old paper mill. And there's, you know, there's about $15 million worth of buildings sitting empty. There's 2 different power grids, 60,000 horse switches for 2 different power grids, a water main, a rail yard, all this stuff sitting unused. And my idea is that we need to revitalize these systems. And then right next to it is all this biomass rotting. And I guess, so you can see kind of all the biomass around. And then I built a machine, which we can just look at really quick. So I use gasification to drive my pyrolytic retort. And this is the machine right here that I built, and that's the gasifier, and that's how I make char. And I got thermocouples all over it, so I'll leave those names up there. So I can tell what I'm making, basically. I have a high degree of control over the temperature and a provenance of the material, so when I make it, and when we do the research, we can have an understanding of why it's doing what it's doing.
And it's made in a batch, and then it's done, and you move the batch over as it continues.
It's like semi-continuous, I guess. I put in batches and then I can extract them. I can do it's very dynamic, so I can do all kinds of different things, and that was the point for it. It was that control.
So the last thing you said was really interesting about combining this process with other processes that have other infrastructure. So if you could find like the ideal partner to aggregate this to, then for incremental effort, they could get a much bigger potential yield from the combination of what they were doing and what you were doing. So who's your ideal partner? What would be
Biogas.
best to glue this onto?
It's biogas. That's
Biogas.
the clear partner is biogas, because if you're looking at a methane digester, what they have is they've got extra heat, right? But generally, if they're putting in, they've identified some heat users they need that we could maybe flood some of our heat back into it. The other thing they've got is this byproduct of a nutrient-dense solution, but there's a lot of water into it in that. Now, in order to get that nutrient solution out to a farm field, you're shipping a lot of water, right? And if we've soaked char in that, we can passively extract those nutrients, including the carbon, and all of a sudden we have this this material that's bringing carbon and nutrients to the farm field, and without the water as much. And that's a really beautiful system in my mind, and that's where it works really well. And anyways, yeah, that's what I've identified as the perfect co-locator.
So have you guys been targeting biomass people to go after to team up with?
Yes. Yeah. This is what I want to talk about here.
Okay.
This would be a good time to
Yeah.
pass it over.